Welcome back to the channel. Today we're diving into one of the classic experiments in physics, the Atwood's machine. It looks simple, but it beautifully demonstrates Newton's laws of motion. What is Atwood's machine? An Atwood's machine consists of two masses connected by a string that passes over a pulley. Imagine two weights, M1 and M2, hanging on either side. Gravity pulls them down, but because they're connected, their motion is linked. Let's look at the physics behind this system. The system is composed of a pulley, a string, and two masses. We assume that all these objects behave ideally. The pulley is rigid and does not deform under the tension of the string. The string itself does not stretch, and its mass is negligible compared to the masses attached to it. As the masses move, the string does not slip over the pulley. We also neglect air resistance, meaning that gravity is the only force acting on the masses. Finally, we analyze the system from a non-accelerating reference frame. These are idealized assumptions, but they provide a very good approximation of real physical systems. With these initial considerations established, we can now begin analyzing the problem itself. Here we have the force diagram for Atwood's machine. The mathematical framework we use is vectors, because Newtonian mechanics is formulated with them. Observe that the system starts in equilibrium. Gravity acts on both masses downward, trying to pull them, while the string resists and produces tensions T1 and T2. This is the initial configuration before motion begins. Because the masses M1 and M2 are different, after this instant, the heavier mass will pull the lighter one through the string. In this case, M2 is greater than M1. Both masses are initially at equilibrium and have zero velocity. When the system moves, since M2 is greater than M1, the left mass rises while the right mass descends. Remember that the string is inextensible, so the distance traveled by the left mass equals the distance traveled by the right mass. Only the directions differ. The same applies to their velocities and accelerations. For the left mass, we have weight m1g downward and tension T1 upward. The net force on m1 is upward, so its acceleration is positive because it points in the positive ZE direction. For the right mass, we have tension T2 upward and weight m2g downward. The acceleration here is negative because it is opposite the positive Z axis. The magnitudes of A1 and A2 are equal, only their directions differ. Substituting the third expression in the first, we have a new first vectorial equation. These expressions give the net forces for both masses. But notice we have three unknowns and only two equations. How do we solve that? The answer lies in the assumption I mentioned earlier about the string's mass. We assume the string is massless, or its mass is negligible compared to the two blocks. That assumption allows us to conclude that the tensions T1 and T2 are equal. With that, a simple question arises: why are they equal? Suppose the string had mass. We could divide it into small pieces, each with mass dm. As the blocks move, the amount of string on the right would become greater than on the left and would increase over time. The weight of those pieces would affect the tensions on each side, changing T1 and T2. That is why, for simplicity, we assume the string is massless. Now that we've solved the unequal tension problem, only two unknowns are left, T and A2, and we have two equations, so we can find them. If we subtract the first equation from the second, the tension cancels and only A2 remains. Solving it gives A2 in terms of the two masses and gravity. That's neat. Assuming the string isn't massless, the only inputs we needed were the masses in G, so A2 depends only on those. Observe that whenever the mass m2 is greater than m1, the numerator is negative, and the acceleration vector A2 is always downward. That is why the block 2 falls. Let's look at two simple cases related to the acceleration A2. First, if the masses are equal, m1 equals m2, nothing accelerates. Gravity pulls both the same way, so the system just sits there. With equal masses, the setup stays unchanged. In the second case, imagine one mass goes to zero, say m1 equals 0. Then m2 just free falls with acceleration g downward. That makes sense because there is no mass m1 to pull the mass m2 through the string. Does that match what you expected? Now for the tension T. Once we know A2, we can plug it into one equation to get T. It also depends on the masses in G. The two special cases again make this clear. If the quantity m1 is equal m2, the tensions are equal and balance gravity, so the system is stable. In other words, each tension matches the corresponding weight. This last expression is clearly Newton's third law together with the state of equilibrium of the system. If the scalar m1 is 0, then the block m2 free falls, and the tension disappears. As we can see, it is clearly predicated through the equations. You need two masses pulling the string under gravity to create tension. With only one mass attached, the other side is free and the string isn't under tension anymore. So that's the Atwood's machine, a simple setup that unlocks the secrets of Newtonian mechanics. If you enjoyed this explanation, don't forget to like, subscribe, and share it with your friends. Thank you for watching, and God bless you.